algebra students. Today we're going to continue looking at patterns, and we're going to find some different patterns of change. So not just the linear patterns that we're used to, we're looking at different kinds of patterns as well. So in this warm-up problem, I've got 4 different ways to look at this shape over here that's made up of all these smaller squares. So I'm going to move it so I can see all 4 expressions and see the shape. When I look at expression A, what they have here with this subtraction, they're really saying that I've got this 6 by 8. I want you to notice this is 1, 2, 3, 4, 5, 6 tall on that longest part, and 8 is 1, 2, 3, 4, 5, 6, 7, 8. So if I just had a 6 by 8, that would be an entire rectangle. However, I don't have an entire rectangle. I have this part over here that kind of got cut off. That's the 2 by 3 part because it's too tall and 3 across. These 6 squares that would have been in here have been taken out. And that's one way of looking at this area. The next one, if I would look at 4 by 8 first, remember we said that it was 8 going this way, and 4 by 8 would give me all of this rectangle right here. Then the 2 by 5 would be 2 tall and 5 across this way. So that would give me that. And if I would add those 2 smaller rectangles together, it would give me the bigger shape. For expression C, very similar. I've got 8 plus 8 plus 8 plus 8, 4 of those 8s, and then 2 5s. So here's one row of 8, 2, 3, 4. And then I've got 2 rows of 5. I also want you to notice that these 4 8s would be like this part right here, and these 2 5s would be like that part right there. The last expression that they have there, that 5 by 6 plus 3 by 4. The 5 by 6 part would be looking at, remember this was 6 tall this way, and this is 5 across this way. So this would be the 5 by 6 part, and then the 3 by 4 part would be this one right here. So again, 2 separate rectangles that they could add up. So I want you to notice that there's lots of different ways of writing this same expression for the area of that shape. Today we're going to be looking at lots of patterns, and a lot of times they draw these dot patterns that you should be able to figure out what's happening each time. It may be difficult sometimes to put it into words, but most of the time I think you'll be able to figure out exactly what's happening. So I want to look at these 2 different patterns of dots and figure out how each one is changing. So in pattern 1, I have 1 dot. That's step 0, and I know that step 0 is kind of weird to talk about, but we will be talking about that eventually. Step 1 then has 3 dots. Step 2 has 5 dots. Step 3 has 7 dots. In pattern 2, I don't have any dots in step 0. Step 1 is 1. Step 2 is 4. Step 3 is 9. So when I look at how the dots are changing, in pattern 1, I can see that this is a linear pattern, right? We're adding the same amount every time. It's a constant rate of change. So if I wanted to find the 5th step, I could just continue my pattern. I could say, well, in the 4th step, then I would have 9, and then in the 5th step, I would have 11. Here's another way to see this instead of just having to count through every time. Let's look at let's start with step 1 actually. In step 1, I've got a column right here of 2 dots plus 1 extra. In step 2, I've got 2 columns of 2 dots. So that's the 4 plus 1 extra. In step 3, I've got 1, 2, 3 of those columns of 2 dots. So that's 6 plus 1 more is the 7. So for the 5th step, I would have 5 of those groups of 2 dots plus the 1 extra. That's how I could get the 11 that way. Looking at pattern 2, and actually I should go back for a second. On pattern 1, step 0, I have 0 rows of those columns of 2. That's why there just isn't a column of 2 there. In pattern 2, I'm hoping you're recognizing, first of all, that this is clearly not linear. I'm not adding the same amount every time. To go from step 0 to step 1, I'm adding 1. And then to go from step 1 to step 2, I'm adding 3. Then step 2 to step 3, I'm adding 5. So there is a pattern that I can see with what I'm adding, but I'm not adding the same amount every time. So it's not linear. It's also not what we call exponential, where we're multiplying by the same thing every time. That's not what's happening here either. But I'm hoping that maybe you recognize these numbers. That, let me actually start here with step 2. 4 is really 2 squared. 3 squared would be 9. 1 squared is 1. And in fact, 0 squared is also 0. So if I wanted to find the 5th step, I wouldn't even have to do the 4th step. I certainly could. 4 squared would be 16. But on the 5th number of dots in here for the pattern, that would be 25. It's just that number of the step squared. Squaring numbers today is going to be really common when we're looking at our patterns. So we already have this pattern. We just already figured this out. So in pattern 1, step 0 had 1, and then we had 3, 5, 7. This was 9, 11. Now, without drawing out and without counting out all the way, step 10 would be 10 of those groups of 2. So that's 20 plus 1 would be 21. So the way that we could write the pattern for any number of steps would be 2 times the step number plus the 1 extra. When we look at pattern 2, step 0 had 0. Step 1 was 1, and then 4, 9. We talked about 16. Here would be 25. A pattern of the 10th one in this pattern would be 10 by 10 square, so that would be 100. And then for whatever term I want, I would just take whatever step I'm on and square it. When I look at this, so this is the table that we just filled out. If I graph this, and you'll have to just bear with me a bit as I'm graphing this, for pattern 1, for the dots. So 0 is my step. I would have 1 dot there. Step 1, I would have 3 dots. Step 2, I have 5 dots. 4, 3 is at 7. 4 is at 9. 5 is at 11. Right? And you can see, even without this being perfect, you can see that this is supposed to be linear. It had a constant rate of change. I'm actually going to use a straight line so that I can do a better job of graphing that for you, even though my points weren't perfect. That is a straight line. For pattern 2, this is not going to be a straight line. If I can move the right thing, that's what I'm looking for. Step 0 was at 0. Step 1 was at 1. 2 is at 4. 3 is at 9. So already you can see it's clearly not linear. 4 is going to be at 16. 5 is at 25. Right? So, and I don't have space for the 10 on this one either, but when I draw this, and I'll just do my very best, off by a little bit, but you can see this is definitely a curve as we're moving up. So not a linear kind of a function. And what's really happening is it's increasing faster as we go. So the rate of change, so for instance, here the rate of change from here to here is 3, and then this is 5, 7, 9, right? So it's increasing faster and faster as we go because of that squaring that we've been talking about. And here it is graphed better than my graph. But the question here says the points representing the first pattern line because going from one step to the next is adding. So that's a constant rate of change, right? The points represented in the second one do not lie in a line. They're in a curve because they're increasing faster as we go from one step to the next. Here's another pattern of growth. So this first question just says, is this a linear kind of a growth? So let's just look at how many we have in each step. In step 1, I just want a different color. I have 3 of those squares. In step 2, I've got 6 of those squares. In step 3, I've got 1, 2, 3, 4, 5, and 6 more is 11. So clearly not linear, right? It's not a constant rate of change. There is a pattern, and I hope just looking at this you can see a pattern, and I'm going to give you a hint on what that pattern is. I am just going to shade in something here so you can see it maybe. So in the first one, step 1, we have just this 1 in the middle, 1 squared plus these extra 2 on the sides. For step 2, I have this 2 squared makes a square. That's a 2 by 2 square plus those 2 extras. For step 3, I've got 3 squared, and then I've got the 2 extras. So let's take a look at that. Step 1, again, we had 3, and then we had 6, then we have 11. So thinking about what the next one would be, right? We said that whatever this kind of middle section is right here, this was 3 squared, and then we added the 2 extras on the sides. So if I do 4 squared, that'd be 16, plus the 2 on the sides would be 18. 5 squared, so a 5 by 5 squared would be 25, plus 2 more would be 27. 10 squared would be 100, plus 2 more is going to be 102. 12 squared is 144, which you should know, and then add 2, I'm going to get 146. So my pattern this time, if I want to know for any particular step in this, I would take my step number and square it, and I'm going to add 2 more to that for those extra, like these wings that are out on the sides. So here's the table that we just figured out. And step 3, or question 3, is asking if the number of squares is growing exponentially. Now, I've mentioned exponential growth just earlier in this. Exponential growth means that I'm just multiplying by the same thing every single time. And I want to see if that's really happening. So to go from 3 to 6, for instance, I'd multiply by 2. Okay, does it keep going like that? 6 times 2? Oh no, that's not 11. I don't even have to bother, keep going, because it's not multiplying by the same thing every time. That's what exponential growth is, even though we haven't really studied that yet. Here's another one that we're looking at, and I want you to notice we've got like dashed lines here and here, like those are the pieces that are missing from this. So in this, Han wrote n times n plus 2 minus 2 times n minus 1 to find the number of small squares in this design for whatever step we are. And it says, explain why Han is correct. This is correct. When we look at this, I'm just going to pull this sideways because it'll maybe be better than me just trying to write this out on here. I want you to see this. So the shape that we had here, if we call this side n for whatever step we're on, there's 2 extra squares going this way, right? If it was just n by n, it would be, let's say, like a 3 by 3 or a 4 by 4 or a 5 by 5. But this is just, n is just whatever number we happen to be on, but there's 2 more columns going in one direction. However, it's not a full rectangle. If n is this full side length, then I'm going to be taking off these 2 squares here and these 2 squares here. And that's going to be this n minus 2 of these n minus 1s that we've got. This whole thing is n. I'm taking away these 2, but I want to see how many I'm taking away. I am not taking this one. I'm taking this much off. So if I would take the length of n, which in this case was 3, and I would subtract 1 away, that means I'm only taking away 2 on this side and 2 on this side, but it is happening twice. That's what that 2 is for. Now, that's one way to explain this. And I'm not going to lie, I think that it's kind of a difficult pattern to see in that way. It says label the picture. We were just looking at that picture. There are different ways to explain this, and you may have chosen a totally different way than this for explaining this area. But that's just one way to look at it. Okay, so right now, I want to think about the relationship between the step number and the number of small squares. In some of these different patterns. So for instance, in this pattern, this is a different kind of growth than what we've looked at. This is clearly not a linear growth, and we even said it's not an exponential growth because it's not multiplying by something every single time. I've already kind of hinted at this. To know the difference between how many squares we have and how it's different, how it's been in some of our other patterns before. This is not where we're changing by the same amount every time, so it's not linear. The graph that we're looking at on some of these, it's not going to be a straight line. Okay, so that's how it's not linear. The second question says, how would you describe a quadratic relationship? Now, see how it's in quotes because we haven't really used that word yet. A quadratic relationship means when something is being squared. So we haven't used this word yet. And I know that a lot of people see the word quadratic and they want to talk about 4 of something. But quadratic in math is really just talking about when something has a squared relationship. So if we want to be able to talk about that with someone that doesn't know anything about this, it's when we are not changing by the same amount, like a linear kind of a constant rate of change, and we're not multiplying by the same factor. It will be a curve, and that curve, we've only looked at part of these kind of graphs. It's either starting out slow and then it's increasing quickly, or we can have some graphs that go the other way, where they are maybe decreasing very quickly and then kind of slow down depending on the part of the graph that we're looking at. But if we look at the whole graph on some of these, which we haven't yet, you're going to see that these graphs are going to be increasing and then decreasing, or decreasing and then increasing. So very, very different from a linear graph where it's just going in one direction and it's got a constant rate of change. Here's the other important word right there. We are going to be looking at things that are getting squared in our equations. So for this cool down now, looking at these 3 different patterns, it says which pattern shows a quadratic relationship between the step number and the number of dots, and explain how you know. So let's just take a look at what our numbers are doing here, what our dots are doing here. In pattern A, we have 0 in step 0. In step 1, I've got, let me be writing these down. Here I've got 0. Here I've got 2. Here I've got 4. Here I've got 6. So think about what's happening here. Clearly, we are just adding a constant rate of change every single time. It's increasing by 2 in every step. Or we could even say that the step number is being multiplied by 2, right? 0 times 2 would be 0. 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. In pattern B, for step 0, I have 1. Step 1, I have 2. Step 2, I've got these 4 here and then 1 more, so that's 5. Here I've got these 9 plus 1 more is going to be 10. So clearly not a linear pattern, right? We've looked at patterns like this already, and I'm going to come back to this one because I want to be looking for a square kind of a relationship. In pattern C, I've got step 0 is 1, step 1 is 3, step 2 I've got 9, Step 3, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 by 3 is going to be 27. So take a look at what's happening here. This is not increasing by a constant rate. However, if I multiply each one of these, if I would multiply this by 3, I would get this answer. And if I would multiply that by 3, I get this answer. And if I multiply that by 3, I get this answer. So this was what's called, because it's going by the same factor each time, that's an exponential growth. Grows very, very quickly. You can see that we get a lot of dots real quickly. So back to my original question of which one of these is a quadratic relationship, that's going to be pattern B. And again, I think it's almost easier to start where we've got a little bit more to work with here. In step 3, I've got this 3 by 3 square plus an extra. Step 2, I've got a 2 by 2 square plus an extra. Step 1, I just have this 1 by 1 square, I guess, which is just 1 plus 1. Here I've got a 0 by 0 square plus 1 more. So I do have that pattern. And what that would be the step number squared plus 1 more. And again, because of that square right there, because of that exponent of 2, that's what makes it a quadratic relationship. So here we've got, this slide has kind of a lot of questions, so I want to try to get as much as we can at a time. We've looked at patterns of change that are not going to be linear, where we're adding the same amount every time, or exponential, where we're multiplying by the same amount every time. So we are looking at things and they're going to end up getting something squared, and then sometimes we'll be adding or eventually maybe subtracting something from that. It says the number of small squares increases by, let me move it so you can see. This increases by 3, and then it increases by 5, and then it would keep increasing with this changing kind of a pattern. So it says specifically, it is definitely not linear because it's not changing by the same amount. It's not exponential either because it's not increasing by the same factor. So when we look at those factors, I could look at this and say, oh, to go from here to here, what would I multiply by? Or usually we say this number divided by this number. So to go from here to here, I would multiply by a factor of 5 over 2. But to go from here to here, I would multiply by a factor of 2. Clearly not the same. They don't match, that just means that it's not exponential. So from our diagram then, we had that 2 by 2 square plus the 1 extra small square. Then we had a 3 by 3 square plus the 1 extra small square. So that's where we came up with this. Again, that's quadratic is what that's called. And because it has that square on the variable, that's what we're looking at for quadratic. Okay. So make sure you check Schoology for this, but we're going to have another cool down lesson. And then on the practice page, we've got a couple more problems for you to try out. So let your teacher know if you need some help.